name is Frank Sanders. I'm the head of the Telecommunications Theory Division at the Institute for Telecommunications Sciences, a laboratory of the National Telecommunications and Information Administration, NTIA, located in Boulder, Colorado. Over the past 30 years, we've developed a series of techniques for measuring emissions from various types of radio emitters. In particular, we've developed techniques for measuring emissions from radar transmitters. In this series of talks, I will begin by describing the fundamentals of RF measurement techniques, and I will culminate the series by describing our techniques for measuring emissions from radar systems, techniques that hopefully you can implement yourself. Accompanying this series of talks are notes available on our website and also NTIA reports that you may find useful. We hope that you will enjoy watching this series of videos as much as we've enjoyed producing them. Welcome to IT...
No, start over. You're too loud.
Welcome to ITS RF Measurement Seminar number 13. Today's topic will be methodologies and results of NTIA broadband spectrum surveys. We're not going to be looking at the results of particular surveys for particular purposes, but rather looking at how NTIA has historically and does currently perform broadband RF spectrum surveys. And by the way, here on the opening slide in the mosaic, this was the original SMS system that used a computer with core memory that had 64 kilobytes, 32K words of core storage. This was the original RSMS-1 and later RSMS-2 in a Travco motorhome. This was the RSMS-3 on a landing craft going out to an island in San Francisco Bay to do a survey. The current RSMS-4, a Suitcase System being deployed out of a Black Hawk helicopter, and the original Department of Commerce radio spectrum measurement system going all the way back to 1927. We'll see more of those here in a minute. So, by way of introduction, I always like to acknowledge the fact that when NTIA and its predecessor organization were talking about what they should do with a broadband computer-controlled radar measurement system back in the mid-1970s, there was a debate as to whether the capability in the system ought to be used more for enforcement purposes or whether it should be used more as a research tool to improve federal spectrum management. And the decision was made to use it primarily as a research and management tool, a tool that can be used to understand how spectrum is being used, a tool that can be used to resolve interference problems. And from that day to this, that's really been the primary emphasis, primary focus of the radio spectrum measurement system. And given that this was the administrative focus, on the technical side, the focus from day number one has always been on computer-controlled measurements with well-designed RF front ends. It was determined early on that trying to do measurements with manually controlled systems is a very inefficient way to do things, and there are a lot of benefits to be accrued from computer-controlled measurements, especially when you're trying to measure across a wide swath of spectrum. So in the modern era, the first system was designed and built by Hewlett-Packard and by engineers here at the Institute for Telecommunications Sciences in Boulder and also at the Office of Spectrum Management in Washington, D.C. These are called the Radio Spectrum Measurement System 1, and later in the same vehicle, a whole new system called the RSMS-2. And the original system built into this Travco motorhome was built as part of a team effort with the Hewlett-Packard company in California. Now, subsequent versions have also been built. The RSMS-3 was built on a pickup truck chassis, and the current version, RSMS-4, is contained in a custom-built truck, and then over the years, various suitcase configurations have been used as computers have gotten smaller and measurement hardware has gotten smaller and more compact. I do like to acknowledge, as I said, going all the way back to 1927, the original Department of Commerce radio car. The lettering on the side of this vehicle says U.S. Department of Commerce, National Bureau of Standards, and this vehicle was outfitted to do radio measurements in the 20s with many of the same capabilities as we have maintained in the systems that were basically resurrected from the 1970s up through the present. Which is to say, it's a vehicularly mounted system. The measurement equipment is contained in some kind of a box-like configuration in the back. The system has a telescoping mast I don't know how high this particular mast went. It's got reasonably high clearance. It can be driven into a lot of different locations. And this is some sort of a direction finding antenna, and we still have antennas that can be used for direction finding, and I would guess that this system probably had a number of antennas that could be used, as in fact we have a variety of antennas that we can use with the system today. Now, starting in the mid-1970s, when the Department of Commerce decided to resurrect this kind of capability, as I said, the system that was designed was contained in 5 racks. These are 3 of them. The other 2 racks would be behind the photographer in this picture. This was the so-called radar system. The so-called land mobile radio measurement system occupied 2 racks up at the front of the van. This is looking toward the back of the van. Here we have the computer, which had 64 kilobytes of memory, 32K words in magnetic core, and it took 2 people to lift it. The programs were loaded on magnetic cassette tapes. This was the CRT and the keyboard for interface. All of the RF hardware was built in here in a set of boxes that went up in frequency in octaves. We had analog to digital and digital to analog converters. Each of these boxes was a full 19-inch rack mount, one for A to D and one for D to A. This is a control for the direction finding system, and then we have some other auxiliary boxes down here. And the land mobile radio system was similarly configured. The RSMS has always had a safe on board so that we can handle the government master file if we need to in the field. And the whole thing was built into an RF shielded motorhome and had a 30-foot high mast that actually was hinged right here and went up and down with an electric motor that drove a big screw assembly. And then we had a direction finding or parabolic antenna that we could mount here. So it was a reasonably serviceable system. Had a pair of air conditioners up on top, had generators down here below. Later we took off one of the air conditioners and one of the generators and put a generator on one side down here and the air conditioner on the other side just to reduce the weight and get the center of gravity down a little. We also had cavity back spiral antennas used for direction finding on radars. 2 generations of measurement system went into the Travco, and then the 3rd generation measurement system went into an entirely new vehicle, which is very much of a box configuration on the back of a pickup truck, actually in many respects closer to the 1927 radio car configuration than the Travco was. 2 telescoping masts, capable of mounting dish antennas, log periodic antennas, etc. In all of these systems we have a high-performance RF front end, and we've talked about good design for RF front ends in other talks in this series. Basically, the RF front ends in all of the RSMSs from the 70s up through the present have noise diodes for calibration. They have variable RF attenuation settings. They have a set of bandpass and yttrium iron garnet tunable bandpass filters and a set of low noise amplifiers which are used to overdrive line loss down the mast until we come down into the measurement system. In the RSMS3 we had 2 independent measurement systems, each of them based on a Hewlett-Packard 8566B spectrum analyzer. This is a typical spectrum survey mode. In this particular case, the van is sitting above Los Angeles. We have a log periodic antenna looking out over the LA basin. It has reasonably high gain, 6 dB over isotropic out toward the basin. It has low gain back behind the van, but that's fine because there was nothing behind the van except some mountains. And then at higher frequencies, we're using an omnidirectional antenna at frequencies above 1 gigahertz. We have a parabolic dish antenna for looking at individual emitters. The current RSMS system is built into a custom-built box on the back of an even bigger truck. Again, very much similar to the 1927 system, except simply bigger. Again, 2 masts, 1 mast here and a second mast back here carried on the rear. Air conditioning, 3 full-height 19-inch racks inside. And really all the capabilities of the RSMS3, but with more interior space and with a new generation of measurement system inside. Now, as measurement hardware and computers have gotten smaller and lighter over the years, we've also been able to set up any number of suitcase systems. And here we see a suitcase system operating up on a skyscraper rooftop. Here is a suitcase system being deployed out of a Black Hawk helicopter. Here is a suitcase system being operated out of the back of a rented minivan. And although you can't see the measurement system here, this is a location on the roof of the National Cathedral in Washington, D.C., where we were using a suitcase system to do specialized measurements. In every case, the systems are similar or common to each other in the computer software that we're using and the measurement algorithms that we're using, and what we typically do is swap out the actual hardware that we're using in any given measurement system, but we typically will use the same software for whatever measurements we might be doing at any particular location. So what are the reasons for doing spectrum surveys? Well, they can be used to establish spectrum usage patterns, such as, for example, the maximum, the minimum, and average levels of activity on a frequency-by-frequency basis across whatever the range of the spectrum survey is that we're doing. They can be used to resolve ongoing RF interference problems at specific localities by looking for signals in the environment and looking for particular signals that might be causing interference at a particular location. If we were doing that, of course, we would actually go to that location because RF interference had been reported there. They can be used to identify unauthorized usage, and in the early days of the RSMS in the 70s, people thought that this might be a prime use for the system, but based on the results of our spectrum surveys over the years, we've actually found that unauthorized usage is probably a fairly rare event at most times and places in most frequency bands, at least in the United States. We have reports that in other countries this may be more of a problem, but in the U.S. people are pretty law-abiding in terms of the use of the spectrum, apparently. In particular, over the years, we've used the spectrum survey results to provide information for spectrum planners and people who are planning new spectrum systems, and we've gotten these results out in NTIA technical reports. In particular, we've gotten broadband survey results. This is for 108 megahertz to 19.7 gigahertz for Denver, San Francisco, Los Angeles, and San Diego, and we've done land mobile radio reports where we actually don't just look at usage patterns, but look at percentages of time that channels are used in land mobile radio bands. And we did this for the Atlanta Olympics, and we've done it just recently for spectrum surveys with the RSMS-4 in Denver and in Washington, D.C. These are all available on the ITS website. When we're going to do a spectrum survey, we don't have a lot of requirements because the system itself is contained inside the vehicle, or if it's a suitcase system, we'll put it inside a room, but these are the requirements that we do have. We're generally looking for some good radio horizon, in other words, a nice clear line of sight, typically at the top of a high hill or a mountain. Suitcase systems may be located on rooftops. If so, then the system's mounted inside a room on the rooftop or near the rooftop, and then we'll run cables out to antennas that are actually up on the roof. If possible, we try to get commercial power. The RSMS-4, though, has diesel generators and really large diesel tanks, so it can run for days on and even weeks on end, just on its internal power generation systems. And we do look for either no or as few as possible strong transmitted signals that are in the immediate vicinity of the measurement system. Now, we do this because we want to avoid overloading our own measurement system RF front end. If there are strong signals that occur, we try to find a site where those signals are not in a band in which we're doing measurements. If we do have strong local signals in the same band we're trying to do measurements, that makes a spectrum survey very difficult, even impossible, because we're basically being saturated or overloaded, or maybe close to saturation or overload, due to the strong ambient signal that's coming from a source right next to us. Now, this requirement is a little bit contradictory to this requirement, because typically in places where you have a good radio horizon, you have transmitters located. But we've always been able to find good sites where we can meet both this first and this third requirement. And then we try to get reasonably good site security, something with a fence if possible. Although again, we've always been able to avoid problems over the years. So what kinds of measurements do we do when we're doing a spectrum survey? Well, first of all, we have swept mode measurements. And as the name implies, and we've talked about these types of measurements earlier in this seminar series, the basic strategy here is to sweep in time across a frequency range. With a conventional spectrum analyzer, we're sweeping an IF. And this is basically the most basic of all spectrum analyzer modes. It does mean that if you're measuring this way, you have a limited amount of dynamic range, typically something like 60 dB, depending upon the spectrum analyzer's characteristics, and for that matter, the characteristics of the RF front end. But this is a good method if we're taking a quick look at spectrum. It's also a good method if we're trying to monitor amplitudes and observe modulation envelopes of a fairly high duty cycle signals, such as land mobile radio, digital radios, point-to-point microwave links. It's not such a good approach if we're trying to make measurements on low duty cycle signals like, for example, radars. But when we're doing a broadband spectrum survey, a computer-controlled system that can repetitively move through the bands and keep all the measurement parameters consistent from one measurement to the next is a very powerful tool. It allows us to schedule surveys with band timing in advance. It allows us to do measurements 24 hours a day, and it allows us to analyze the results without having to worry about whether we were changing the measurement system parameters as we went through the measurements. So computer control has always been very, very, very important to us. Now, if we're making swept mode measurements in a land mobile radio band, or for that matter, an aeronautical mobile radio or marine mobile, in other words, any mobile radio band, then, although we can do measurements to show the maximum, the minimum, and the mean levels of activity across the band for the duration of the survey, we can also make measurements that show the percentage of time that individual channels are occupied in these bands. The classic method has been to use a conventional swept IF spectrum analyzer design, but with the RSMS4, we've implemented a newer approach, and you'll see this if you download the LMR survey results for Denver and Washington, D.C., in which we're basically doing fast digitizing measurement approach, an FFT-style time domain approach, which allows us to quantify the actual percentage of time that the LMR channels are used. And that newer approach allows us, in a nutshell, to do better and faster rejection of bad data. In other words, to identify and get rid of data that was taken in situations in which, for example, some kind of overload was occurring on some of the measurement channels. There's a lot more to it than what I'm saying here, but this is a fast overview of the entire problem. As I say, you can always download the reports to get more information on the particular technique used. I will mention that if we're doing the conventional measurements, or when we were, I don't think we'll do any more of these, but when we used to do conventional swept IF measurements, we actually inserted specially modified bandpass filters into the spectrum analyzer's IF, and these had a rectangular shape that was well suited to isolating the activity of each land mobile radio channel from adjacent LMR channels. Then we have stepped mode measurements. We've talked about these types of measurements again earlier in the seminar series. In these measurements, the strategy is to step, not sweep, from frequency to frequency across a given measurement range in a series of 0 hertz time slices. And this is a sophisticated mode in that it requires computer control of the spectrum analyzer to make a measurement in time on a frequency and then step to the next frequency. But it allows us to interactively vary the attenuation at the front end of the measurement system so that we can take the instantaneous dynamic range of a spectrum analyzer of about 60 dB and add up to about 70 dB of front-end attenuator dynamic range to get a total of as much as 130 dB of dynamic range. And this is particularly useful in the radar bands, where the radars are low-duty cycle emitters and where we want to get a lot of dynamic range on the emissions. But it also has applications to various other miscellaneous types of transmitters, even, for example, measurements in microwave oven bands. As I just said, extended dynamic range is important for measuring individual emission spectra. It's also important in spectrum surveys. One thing that I should mention is that the NTIA capability in the new measurement software allows for automatic computer-controlled insertion of the attenuation as the measurement progresses. In the old days, when we did a broadband spectrum survey, we would often have to actually manually insert attenuation as we went through a radar band, and of course that's a problem if the measurement's running at 2 o'clock in the morning in an automated mode and there's no one there to do it, and we'll see some results of that in the series. Another technique that we use is called Azimuth Scanning. This is a technique that's used to measure occupancy in point-to-point microwave bands. In this technique, we actually use a parabolic dish antenna mounted on the RSMS, and we slowly rotate the antenna around the horizon while a spectrum analyzer, could be either an old-style analog or a new-style fast digitizing spectrum analyzer, is itself swept rapidly across whatever the microwave band of interest is. So as the spectrum analyzer is sweeping rapidly and the dish is sweeping slowly, we're getting a good look at the horizon through the dish antenna at every azimuth where the dish antenna is swept. So if we move the dish antenna 360 around, we get a good look at the horizon 360 degrees around, but we get to look at the horizon with the gain of the dish antenna. And the trick here is to sweep the band of interest fast enough to cover that entire band while the dish has a given point on the horizon inside its scanning beam width. For example, if the dish beam width is 1 degree wide, we need to get 360 sweeps on the spectrum analyzer within the time that it takes the dish to sweep one time around the horizon. And we'll run the system with a spectrum analyzer in a maximum hold mode with a positive peak detector, and this gives us the envelope of the point-to-point link occupancy in the area with the gain of a dish antenna. It's important to use the dish because point-to-point microwave links have typically or always a high gain main beam and low gain side lobes, and we're typically going to be looking into the side lobes of the measurement system. But by using a dish antenna on our van, we can see the energy in the point-to-point microwave dish side lobes, and so we do get to see the occupancy in the band even though we're looking at a bunch of emitters that are highly directional. And as I say, the effect here is that we get an omnidirectional scan around the van, but with the gain of a dish antenna. One other reason that I wanted to come back to, going a few slides back to the reasons for spectrum surveys, is to resolve interference problems. I'm going to do 3 more talks on how to analyze and assess different types of interference problems that are reported. But briefly, although probably half of the reports of RF interference that we get turn out not to be RF interference, if there's a location where interference has been reported and we need to go there to try to identify the source of the interference, then what we will do is use the RSMS to make measurements through the band of interest, typically with an omnidirectional antenna to try to identify the source, but then we'll try to direction find on the source with a dish antenna, or maybe even by using a null off the end of a dipole to resolve the direction of arrival of the interference. And an interesting upshot of all this is that if a system that's getting interference has an extremely high gain antenna, we'll see a couple pictures of these on the next slide, then the ideal way to measure for the interference source of the RSMS is to deploy the RSMS to that site with a low gain antenna. And I'll show you why in a second. These are 2 different sites where the old Travco was used to find interference problems. We've done this with the other RSMS vehicles also over the years, but these just happen to be a couple of exceptionally good photographs. In both of these cases, these are very high gain antennas, and the people who are operating the receivers at these sites, which included NASA Goldstone at this site and Stanford at this site, reported that they were getting interference into these receivers through these dishes. And of course they say, well, you know, we've got a dish antenna with 200 dB of gain, so how can you possibly measure for the interference that we're getting? You don't have anything like a 200 dB gain antenna. And of course our response is, well, we don't want a 200 dB gain antenna, we want about a 0 to 2 dBi gain antenna. What? Why is that? Well, because given that this has a 200 dB gain, its beam width is a fraction of a degree wide, like this. Same for this antenna, fraction of a degree wide. These antennas are typically, in these 2 cases, aimed up well above the horizon, aimed up into space. What are the chances that the interference source is right inside the beam of either of these dish antennas? Basically 0. And if the source were inside the beam, they could simply move the dish antenna off, the interference would go away, and they'd say, oh, that's where the interference is located. So if they're getting interference into these dishes, the interference has to be coupling in on this dish, for example, down here in the side lobes, or on this dish, back here in the side lobes. If you've got really high gain on the main beam, how much gain do you have on the side lobes? Really low gain. If this gain on the main beam is many dB above isotropic, 200 dB above isotropic, then the gain back here in the side lobes is going to be well below 0 dBi. That means that if we operate a measurement system on our measurement vehicle with an omnidirectional antenna, or maybe a directional antenna, or maybe an antenna that has, say, 2 dB of gain over isotropic, we have far more gain around the horizon and in whatever direction the interference source may be located than does the big dish. And if we have comparable sensitivity in the receiver itself, maybe say a half dB or 1 dB noise figure, which we can achieve, then we'll see the interference in our measurement system much higher above our measurement system noise floor than the people who are operating the receiver on the big dish do. And that's a fantastic strategy if you're looking for interference on high gain dishes. Don't worry about getting a high gain, worry about getting a low gain antenna when you make your measurement. So with that said, let's go ahead and just walk through the results of a typical RSMS spectrum survey. All of these figures are drawn from a particular report, NTIA technical report on the results of spectrum survey at San Diego, California. Our broadband surveys have typically started at 108 megahertz, the reason being that we're not typically or haven't historically been interested in HF frequencies up to, say, 30 or 50 megahertz. And from 50 megahertz up to 108 megahertz in the United States, the spectrum is used by non-government systems, basically FCC broadcasters, television stations, FM radio broadcasting. So that hasn't been a focus. We could make measurements below 108, but we haven't wanted to. But starting at 108 megahertz, we have air traffic control frequencies for voice communications and also nav aids. And here we have a problem in this band, which we had to overcome by putting 40 dB of attenuation in this part of the spectrum, where we were, in fact, being overloaded by a strong nearby transmitter. We couldn't get away from it, so in this part of the spectrum we had to insert 40 dB of attenuation. That meant that our noise floor went to a pretty high level, and we don't get to see much right here in this part of the spectrum, but then from this point forward where our attenuation was out, we were able to get a good measurement of the usage at the location. And here we're doing swept max, mean, and min, swept M3, swept maximum, minimum, and mean level measurements. We're using a sample detector, and we get the maximum power level that we saw during the course of the spectrum survey on one curve. We get the minimum power level seen on any given frequency on the lowest curve, and we get the mean level, and this is a decibel mean, but we could give you a linear power mean, on the middle curve. In this particular case, these data consist of 7,000 sweeps across this frequency range at San Diego in 1995, and we were using a 10 kilohertz measurement bandwidth in this band. And what we've done is to note the spectrum usage on each of these graphs with an annotation up above the band, and you can really see the band edge here. You can see where we go from the nav aids down here to the air traffic control communications up in here, and you can see here that all of these frequencies were not occupied at one time or another, and that most of the frequencies were not occupied a lot, but that virtually all of the frequencies in the band were occupied at one time or another during the period that the survey ran, which was at basically 2 weeks, and 7,000 sweeps in that 2-week period. Wait, sorry, sorry, I skipped one there. There we go. Okay. And now we have the 138 to 162 megahertz band. This is broken up into military land mobile radio, amateur, military LMR, and commercial land mobile radio. By the way, some of these band usages that you'll see here in this talk have changed since 1995, but these were the usages for these bands as of when the survey was done in 1995. So again, we see this kind of activity across these military LMR and commercial land mobile radio bands. These are not measurements of percentage of time that channels are occupied, but as I said, the newer land mobile radio surveys that we've been doing with the RSMS4, which you can download for Denver and Washington, D.C., do contain actual percentage of time that these channels are occupied in the government bands for those two cities. 162 to 174, this is a government land mobile radio band, a federal land mobile radio band, and we see that most of the channels had some kind of activity on them during the course of the survey, which here in San Diego consisted of 52,000 sweeps in this band. We see less activity on the average, and we see that at one time or another, virtually all of these channels were not occupied. The one exception being 162.55 megahertz, which was occupied 100% of the time by NOAA weather radio, operated by the National Weather Service. Basically, that's a broadcast transmitter in that band. So while over the years people have commented that usage in federal mobile radio bands might be lower than they think it ought to be or than they would like, nevertheless, in a band like this in San Diego, if you wait for 2 weeks and you run 52,000 sweeps, you will see that these channels are getting some usage at one time or another on virtually all the channels across the band. Here's a measurement made through a television band. As of February 19th in this country, you won't see many of these signals left anymore because these are analog television channel transmissions where we have video and audio carriers, and then most of the video information is transmitted between the two carriers, and we see here TV channels 8, 10, and 12 are occupied in the San Diego area. We see these features occurring in the interstices. These could either be lower powered signals that are further away, or these could be the result of intermod coming off towers. We try to avoid overloading our own measurement system so that we don't generate these kinds of features as measurement errors inside our measurement system. So take that as you will. But as of February 19th, most of the television signals in this country are going to look like digital transmissions, which will look like band-limited noise that will be about 5.5 megahertz wide inside each of these TV channels, to the extent that these particular channels are even occupied after the DTV transition occurs. 216 to 225. This is, or was anyway, used by maritime radio telephone service and land mobile radio and amateurs. And in this particular case, it looks like the amateurs may have been using their part of the spectrum more than maybe these parts of the spectrum were being used by these other services. 225 to 400, again, these are voice communications. In this case, this band is used for, among other purposes, military air traffic control and military tactical communications. And here we see that we always saw some activity on these frequencies. We also have some radio nav aids operated in this band related to the instrument landing system. Now, 400 to 406 megahertz, meteorological aids. And one thing that you'll note is that when we're doing these measurements, we actually break these measurements up such that the measurements actually do correspond to frequency ranges that are allocated for particular services. So this is only 6 megahertz wide, but because it's allocated for the particular service of meteorological aids, meteorological satellite signals and radiosondes, which are themselves med aids, we measure it that same way. Here, we only took 2,000 sweeps across this part of the spectrum as opposed to the 52,000 sweeps that we took in the 162 to 174 band. The reason is that we were a lot more interested in what was going on in the 162 to 174 band than we were in the 400 to 406. But with a computer-controlled system, you can actually schedule these measurements up, and you can put more emphasis on bands that have more interest and less emphasis on bands that have less interest. There are actually a lot of signals in this band, but if you're sitting on a fairly remote hilltop, you're not necessarily going to see a lot of them in this band. Here's the 406 to 420. This is used for land mobile radio, for federal fixed and mobile systems. And again, we see that a lot of channels in this band were occupied at one time or another during the 2 weeks when we took almost 21,000 sweeps. We don't see as much activity on the average, although we see some that were on enough to actually raise the average. And we see that there were about 4 signals here, 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 and here, and here, which were on all the time. And had we wanted to, although we didn't in this particular survey, had we wanted to, we could have tuned our measurement system to any one of these signals, like say that signal right there, and gotten its particular characteristics and identified the particular source of that transmission. Here's a band that's made with a stepped measurement algorithm in the 42450 radar service. And 42450 megahertz radars are used on both aircraft and ships in the U.S. fleet. We actually got a fairly high level up here on the maximum level curve, and in fact it's such a high level that it actually saturated across there and there and there and there. And if we were to repeat that measurement with the system that we have now, we would automatically add attenuation into the measurement system as these signals saturated, and we would actually have developed peaks on these. But at the time that we did this survey, we didn't have an automatic attenuation feature, and when we were making these particular measurements, which only consisted of 68 passes through this whole band during the 2 weeks that we were there, we didn't have anybody in the van at the time that these scans were made in this band to actually manually add attenuation. But we do have detailed emission spectra for the individual radars in this band, and we know the U.S. Navy is out there operating. And this does verify that the U.S. Navy's activity in this band is actually pretty reasonably high.
Did you use Omni antennas?
The question is, did we use Omni antennas? Yes, for that one we did use Omni antennas. In San Diego, we were actually parked out on Point Loma. And so we had San Diego Bay behind us and the Pacific Ocean in front of us and off to our right. So we could have ships actually all around us. We had potentially signals coming from terrestrial sources ranged about 180 degrees around us. And so yeah, we used Omni antennas out there in Point Loma. And again, as I said, here we used the stepped algorithm that's tailored for radar emissions. That's because we know that the emissions in this band are primarily or entirely coming from radar sources. 450 to 470, now we're back to land mobile radio, this time for commercial. And this is a band where, at least the time that we're making measurements, And in this particular location, it's broken up into transmitters and receivers that are fixed, and then transmitters, receivers that are mobile. So here we have a very efficient way to break up a land mobile radio band as compared to mixing them all up together. And you can actually see the difference between the base stations running here and the mobile units running here, and the mobile's over here. So, and in this particular band, we see that we get pretty high levels on the average across the band, and we have quite a few transmitters that were on all the time that we were doing our measurements. In particular, we see these on in the base unit parts of the band, but we even see in the mobile part of the band a couple that were on all the time. So, and because we had more interest in this band than others, we did 20,000 sweeps through this band while we were there in San Diego. 470 to 512. Now we're moving up into another television band. Again, after the DTV transition occurs in February of 2009, you won't see these kinds of signals unless you're looking at relatively low power transmitters that are an exception to the overall DTV rules in the US. But here we were overloading on this signal down here in the 470 to 490 megahertz part of the spectrum. So we actually snapped in automatically under computer control 20 dB of attenuation in this part of the band every time we measured through here to avoid the overload. And then when we were taking measurements from this frequency on up, our front end band pass preselection was good enough that it was rejecting this energy. It was not overloading on this energy, and so from this point on up in this band, we were able to make measurements without the attenuation in. Obviously, it's desirable to not have to put in this attenuation if you can avoid it, and avoid the whole front end overload problem if possible. But if necessary, if it comes to it, you can put in attenuation as an expedient.
So you broke up this into several sweeps.
Right. So the question is, or the statement is, so we broke this up into several sub-band sweeps, and the answer is yes, we did. Exactly. In fact, we had to, precisely because this transmitter was overloading us. So yes, we had to do that. And so to some extent, you need to tailor these particular parameters for every particular location where you go. Yes, exactly. Here we see the television band from 512 to 806. I'm hoping that NTIA will do measurements like this through these television bands after the DTV transition occurs so that we can get some before and after pictures before and after February of 2009. Here we're going from 512 to 812 megahertz, so this is 300 megahertz of spectrum. So now the individual television signals look really skinny. They're still the same width as they are on the previous slide. We're just looking at 300 megahertz of spectrum here. And by the way, this one little slice right in here is channel 37, which is reserved for radio astronomy. And it was, in fact, believe it or not, fairly quiet. But note that if you're a radio astronomer and you want to work near these high-power broadcast signals, you're going to have good front-end band pass filtering so that you can pass signals in your band of interest for radio astronomy purposes and reject the high-power signals on either side. Radio astronomers have the same problem the RSMS does. And because this is not a very dynamic band, it doesn't change a lot, it's a non-federal band, we only did 5,800 sweeps across the whole band while we were in San Diego. But there you are. Now, 806 to 902, this is the old analog cellular band. Uses have changed for this in different times and places since this measurement was done. But here we see LMR mobile, cellular mobile, LMR base, and cellular base parts of the bands. You can see that in a certain sense, this band is probably really quite nicely managed. These are really sharp, distinct edges for the different types of activities in these different bands. And where it says AM, that's aeronautical mobile. And sure enough, we see some weak signals in there, but we don't see these other signals getting into the aeronautical mobile band to any great extent. But because this is, again, is not a very dynamic band, and we didn't have a whole lot of interest in it, we only did 4,000 sweeps while we were in San Diego. 902 to 928, a so-called junk spectrum band, industrial, scientific, and medical. Sort of you name it, it's in here if it's a Part 15 device. For example, baby monitors, but lots of other things on top of that. And this is the band as seen when we're doing the swept measurement algorithm with a maximum hold detector, and we get max, min, and min activity. We could look at these particular transmitters at this location if we wanted to. We have found that when we look at these ISM bands, they vary in their characteristics and behaviors a great deal when we go from point from locality to locality across the U.S. A band like this, the previous slide, this will look pretty much the same everywhere you go unless the use of the band itself gets changed at some point in time. But in a band like this, you can go 5, 10, 15, 20 miles, and you'll see an entirely different pattern of usage as we documented in our San Francisco spectrum survey results. Oh, by the way, there are even some old-style microwave ovens. I don't know how many are still operating, but there are or were a few old-style microwave ovens operating in this band. However, this is also a band. Oh, and I said here, yeah, swept algorithm, max hold detection. However, this is also a band which is used by U.S. Navy radars. Not very many, but there are a few in there. So we looked at the band also with the stepped measurement routine in a 1 megahertz bandwidth as compared to the measurements that were done with the swept algorithm with maximum hold detector, or maximum hold detection, with a 10 kilohertz bandwidth, and look at the difference in what you see in the band depending upon how you make your measurement. And this is where computer algorithms are really powerful. You can measure it this way and see this activity, or measure it this way and see this activity. Which one would you like to see? Depending upon how you make your measurement, you'll exclude your ability to see one type of activity, but you'll bring into sharp focus your ability to see the other type of activity. So this is an example where you may want to not only tailor your measurement carefully for the band of interest, but maybe measure the band with 2 different algorithms. And again, it's terrific to do this under computer control because it's easy to measure it with 2 different algorithms sequentially back and forth, and see the different types of usage in the band. Here's 928 to 960. This is a band that's been used by a variety of special mobile radio services and systems. 928 to 932 is interesting in that this is where pagers are located. And when we're doing spectrum surveys, pagers can be a real problem because people set up pager systems to get high power signals almost ubiquitously in metropolitan or urban areas. And these signals tend to overload our measurement system. So we sometimes have to go to some extraordinary lengths to try to either notch these out or put in a particular filter to reject this entire band across here, as the case might be. For example, we had pretty high power signals hitting us out there on Point Loma in San Diego. Then we see a variety of other land mobile radio signals. Here we have LMR base stations, for example. And again, we can see how the spectrum uses are pretty segregated. Here, 960 to 1215, this is a band occupied by a variety of aeronautical aids, including tactical air navigation, so-called TACAN, distance measuring equipment, DME, air traffic control radar beacon interrogator systems, where they interrogate at 1030 and the aircraft reply at 1090. We've talked about those in an earlier talk. And also the Joint Tactical Information Distribution System, JTIDS, which is used by the military. These are, in many cases, relatively low duty cycle signals, so they don't raise our levels much on the minimum or the average, but we see that if we look at them with a peak type of response, we see that this band is in fact heavily used by these aeronautical signals. These are in fact the interrogations, for example, for aircraft at 1030 megahertz coming up from the beacon at Lindbergh Field, and these are the aircraft replies at 1090 coming down from aircraft all over the sky. But they're low duty cycle pulse signals, so you don't see them unless you measure with a wide bandwidth with peak detection. 1215 to 1400 used by the long-range radars that we talked about in earlier talks, and we see a whole set of these radars. These are spread out all over Southern California, and we see them all through here, and these are only 28 scans. We didn't look at the band a lot because these radars are pretty much on and running on a permanent full-time basis. But we step across here with a 1 megahertz bandwidth with peak detection using the stepped algorithm, and sure enough, we fill in this radar activity rather nicely. Here, on the average, nobody was present to invoke attenuation, so these averages, like on this radar, are rather low, but we always got at least one scan through here where we did put the attenuation in manually so that we made sure that we did fill out this whole envelope. With the new measurement software that we have, that attenuation will be invoked automatically as we move across the band with the stepped algorithm, and we won't have to worry about doing that manually anymore. 1400 to 1530 used down here for radio astronomy, which is passive, so you don't expect to see a lot there, and sure enough, we don't. And then aeronautical telemetry, various purposes, only 9600 sweeps across there. Not seeing a lot of activity. This band is used more in particular locations than in others in the U.S. Just wasn't being used a lot in San Diego. 1530 to 1710. This is used by a variety of satellite signals, including, of course, GPS, which is broadcast from satellites in medium-high Earth orbits at 1575. There are even more radio navigation satellite service signals in this band now, but in 1995, GLONASS and GPS were the only services out there. With the antenna that we were using on the RSMS, which was a low-gain antenna, we wouldn't see those signals, even though they're being transmitted from the satellites. We do, however, see the side lobes of satellite uplinks in the area, satellite Earth station uplinks, and we are seeing not the main beams, which are aimed up into space, but we're seeing the side lobe energy coming off those uplinks, and we did see some radiosonde activity in there. 17 to 2300. Various point-to-point microwave links. This is a band where we used the azimuth scanning technique. This is where we move a dish antenna slowly around the horizon while we run with a maximum hold mode with peak detection, and we fill in the activity 360 degrees around the horizon with the gain of a dish antenna. And I'll take that back down so you can see what that looks like. So here we're seeing into the side lobes of these point-to-point links. These links all through here are analog links, which at the time were the predominant type of link that people were using. This is a digital link. If we did this measurement right now today, we would probably see a reverse situation. We'd see probably almost all digital links and just a few analog links that are left. And now, 2300 to 2500, this is a industrial, scientific, and medical band, and it is used by most microwave ovens that are operating in the U.S. And here we see microwave oven activity all through here. We see that we always saw a few microwave ovens all the time, even at, say, 2 o'clock in the morning, but that if we look at the total envelope of occupancy, we see this very impulsive, spiky occupancy, and these are microwave ovens. We can verify this by looking at individual ovens in the lab, which we have done over the years, and sure enough, we see that individual ovens emit these kinds of spectra. We also see that we have sort of two modes in the ovens. The magnetrons in microwave ovens typically oscillate between these two frequencies, and they actually slew in frequency in between. It helps to cook the food better, and it's also a result of using relatively inexpensive magnetrons. But instead of seeing the cosmic microwave background radiation, here we see the microwave oven background radiation. And by the way, if you're ever checking a measurement system and you're working anywhere in this part of the spectrum, look for microwave oven signals. If you don't see them, something's wrong, because you should see them if you're sitting out in the open up on a hilltop. Same for the air traffic control beacon signals at 1030 and 1090. If you're working in that part of the spectrum outdoors with a system and you don't see signals, for example, at 1090 coming from aircraft, something's wrong. Because you will see those signals coming from aircraft even if you're in the middle of a desert, because the aircraft will be responding to transponders on the ground that might be 200 miles away. Here's 2500 to 2700. This was another point-to-point band at the time, and sure enough, point-to-point. Point-to-point band at the time, and again, we do the azimuth scanning, and we see all these links. At this time, they were all analog running across there. Here's 2729 air traffic control band for short to medium range radars, airport surveillance radars. Again, we didn't have our automatic attenuation routine running, so the averages got truncated on these radars, but we did always manage to get at least some scans with a person there with the measurement system, so we were able to fill out these spectra. These two frequencies are coming off the radar at Lindbergh Field, for example, and then we have some other radars that are at locations that are further away than Lindbergh Field. And again, with the system that we have now, we wouldn't have to worry about attenuation because the computer would invoke it automatically. 29 to 31, this is used by tactical radars, tactical military radars. It's also used by some maritime surface surveillance radars, navigation radars. There was one that was located shore-based near Point Loma, running at 3050 megahertz, and it was on all the time, and there it is. And then we see these other radars that are running on ships off of Point Loma at different times during the survey. By the way, what you're seeing in all these pictures are composites that show the results, of course, of the maximum, the minimum, and the mean, as I said at the beginning of the talk, for all the scans, in this case 48 scans that were made across the band during the period of the spectrum survey. So this radar may have been on at one time, this radar may have been on at another time, but here we're seeing the total composite aggregate behavior of those radars through the whole time that we were there at Point Loma. Here's another military radar at basically 3150 up through about 3400 megahertz. Some other radar signals here. Here we see a band being used for commercial point-to-point and for fixed satellite downlinks, and we see a couple of digital links in here. We did this measurement with the Azimuth scanning routine. 4200 to 4400, airborne radar altimeters. Remember 2 talks back I mentioned these are the systems that say pull up, pull up, pull up, pull up just before the pilots fly the plane into the ground. These are the signals from the altimeters from aircraft that were on approach or departing from Lindbergh Field that happened to fly basically directly over our measurement system. Most of the time we don't see the signals at all, but every so often we did get a plane that came through that gave us a nice signal there in the band. 4400 to 5000 megahertz, another point-to-point microwave band. Here we see digital, 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 and some analog links. My guess would be at this point in time we'd see mostly digital links if we were to go back and look at this. There are also some satellite uplinks and downlinks in this band. 5000 to 5250, the Great Desert. Basically, we're seeing a little bit of noise in here. Microwave landing system is operated in this band, but microwave landing system, to my knowledge, is currently being used in the U.S. only under ICAO treaty obligations at 2 or maybe at the most 3 airports: New York, Seattle, and I think there's actually one at White Sands Missile Range for the Space Shuttle airstrip. So generally, we don't see anything in this band. Long and the short of it. This is a band occupied by 5,000 megahertz radars, 5250 to 5925. We see a variety of these radars through here. Again, we had our little attenuation problem, but we see that we have activity in here all across the band. Another point-to-point band and fixed satellite link band, 5925 to 7125. So again, we use the Azimuth scanning technique to look into the side lobes of the dishes out there on the horizon with the dish antenna mounted on our measurement system. 7125 to 8500 megahertz, again a government point-to-point and satellite band, again measured with the Azimuth scanning technique. Now we move up into another radar band, 8.5 to 10.5 gigahertz, used for a lot of different types of radars, but a prime use in this band is for maritime navigation and surface search systems. And so these are the small radars that you see on boats up through really aircraft carriers out at sea. And we see that there was one that was shore-based near Point Loma that was on all the time. That's a nice check of the measurement system. But we see lots of other signals from ships that were transitioning back and forth in and out of the harbor and off of Point Loma during the period of the spectrum survey. We only did 23 scans across this band in the 2 weeks that we were there, and just in those 23 scans we got this activity. Also, we do see airborne radars in this band, and we did see airborne radars in this band. So, but we can't distinguish them on that particular graph. 10.5 to 13.25 gigahertz used by point-to-point and fixed satellite systems. Here we had a digital link. We did this as an azimuth scan around the horizon, but not a lot happening based from our measurement location there on Point Loma in that survey. 13.2 to 14.2 gigahertz. Now the pickings become slim. There are systems in this part of the spectrum, but there wasn't a lot out there. This was a system that was off of Point Loma just at one point during the time that we were making our measurements. And a fixed and mobile and satellite services band, nothing. We did an azimuth scan around the horizon, we just didn't see anything there between 14.2 to 15.7. 15.7 to 17.7, this is used by radars, but here's the problem with finding these radar signals. These are typically low-powered radars with very high-gain antennas that are typically mounted on aircraft, so they're sector scanning off the nose of the aircraft. They are often turned off entirely. They transition quickly through a given area, and so although these radars use this part of the spectrum, your chances of seeing them from a hilltop on a chance basis are rather low. Also, we only took 39 scans across this part of the spectrum while we were there, so we didn't see any activity in the band. Not to say that there aren't radars in there, we know they are because we've measured their individual spectra over the years, but you're not going to get a very high probability of intercept on those signals if you're sitting on a hilltop. Still, we go through it for the measurement purpose. And in 17.7, 19.7, fixed point-to-point and satellite, again, we're not really seeing much in there. We are seeing, by the way, here, a little bit of variation in the measurement noise floor of our system. That little step right there is due to a change in the noise floor of our measurement system at 19.3 gigahertz. And that ends the survey range that at 19.7 that we've typically done with the spectrum surveys with the radio spectrum measurement systems over the years. We can go to higher frequencies, but as you get much above 18 gigahertz, things change in the system. For example, you typically have to swap out to a different set of antennas. You sometimes have to change connectors. You may well have to move up into another set of filters and amplifiers at the front end. The attenuators at the front end may not operate above 18 to 19 gigahertz. So given that we already don't see a lot of activity in these bands going all the way back down to about 13 gigahertz, and given that a lot of the RF components have to change, once we get above about 18 to 19 to 20 gigahertz, this is where we've truncated our surveys over the years. That ends the formal part of the talk. Are there any questions or comments?
I've got a question for
Sure,
you.
Jeff.
How do you determine the measurement parameters that you're going to make for when you make measurement on a particular band? The number of sweeps that you use, the resolution bandwidth that you're going to use, whether you use a swept or a stepped.
Exactly. Yeah, good question. Yeah, how do we pick all these parameters and how do we decide how often we're going to look? We tailor the parameters to the types of usage that we believe we're going to see in the band. Now, admittedly, this means that if there were a type of usage in the band that were completely unexpected, that basically were not in accord with the federal and non-federal frequency regulations in the U.S., we might not see the activity. But given that we have looked at some bands with sort of non-standard parameters over the years, and we've never so far seen any, you might say, non-standard, non-legal, non-correct activity, what we do is, first of all, we tailor the measurement bandwidth to the bandwidth of the transmitters in the band. We try to match the measurement bandwidth as nearly as possible to the bandwidth of the transmitters. So radars that might be typically transmitting a 1 microsecond pulse width will use a 1 megahertz bandwidth. Land mobile radio signals that we expect to be maybe 6 1/4 or 12.5 kilohertz wide, especially with the new FFT type systems, we'll actually tailor the measurements to look for signals with those kinds of bandwidth. But the bottom line is that we'll try to use a quote measurement bandwidth unquote, which is as near as possible or as equivalent as possible to those bandwidths. Now, it is true that 6 1/4 is a little different from 12.5, and you might even have some 25 kilohertz, so you might have to compromise, but some bandwidth like that. Detection schemes, if we have land mobile radio, marine mobile radio, aeronautical mobile radio, we'll typically use a swept maximum, minimum, and mean scheme, or we'll use a measurement scheme where we're actually measuring for percentage of time that the channels are occupied, especially with the newer system, as with the measurements that we've just recently published for Denver and Washington, D.C. If we're looking at ISM bands, we might use a peak detector with a narrow bandwidth because those emissions may be rather impulsive, but they're still relatively long pulses. They might be a millisecond or 10 milliseconds or 100 milliseconds long. So there we might be back to something like a 10 or 30 or 100 kilohertz bandwidth for the measurement system to try to match the transmission parameters of the ISM devices. But we'll go just with a peak detector because they still have a relatively low duty cycle, and we're trying to just pick them up well, with a system that's good for getting a low duty cycle signal, which would be a peak detector. And we saw that with the ISM measurements that we made. With the point-to-point microwave bands, we again match the bandwidth to the emission bandwidth of the transmitters. Now that most of these systems, I believe, are using digital signals, we'd probably use a wider bandwidth for future spectrum surveys than we did for some of these point-to-point measurements that you just saw, where we were looking for these narrowband carriers on the older analog links. Although with that said, there's a bit of a trade-off because there's still some older analog links out there. So you get your best signal noise ratio with the analog link with a more narrow bandwidth, your best signal noise ratio with a digital signal with a wider measurement bandwidth. So you may have to make a decision at that point about whether you want to measure it twice, once with a narrow bandwidth, once with a wide bandwidth, or just pick a bandwidth that allows you to get the best possible signal noise ratio with the type of point-to-point link signal that you're most interested in trying to see. So the bottom line, though, is that we try to tailor our measurement parameters to the emission parameters to maximize our signal-to-noise ratio and to maximize our probability of intercept. Now, as for how often we go through the band, if a band is more static and we have less interest in it, for example, broadcast television bands, we won't go through them very many times typically in the course of a spectrum survey because, number one, they're not changing very much from day to day, hour to hour, etc. And number two, we may not be that interested. If, on the other hand, we think that the activity in the band should be highly dynamic, like in a mobile radio band, then we'll make a lot more measurements of that band during the course of the spectrum survey because we're trying to get better statistical numbers, and in particular if we're trying to get a percentage of time that channels are used in a band, then the more measurements we get in that band, the better. And typically we are more interested in the marine mobile, aeronautical mobile, land mobile radio bands, and they are more dynamic, so we'll make a lot more measurements there. This is where measurement scheduling becomes important. With a computer-controlled system, we can actually schedule either the exact times that we want to do the bands, or we can schedule the percentage of times that we go through the mobile radio bands compared to the percentage of times we go through, let's say, the radar bands. And this allows us to tailor our measurements such that we spend a lot of time looking at the dynamic high-interest bands and a small percentage of time looking at the relatively less dynamic, relatively less interesting bands. For the measurements that we did, for example, for San Diego, we actually prioritize the bands as priority 1, priority 2, or priority 3. The priority 1 bands we went through a lot, the priority 2 bands we went through a lot less, and the priority 3 bands we went through basically typically once, or a very small number of times. Anything else?
Now the minimum, I guess, is most helpful just to determine if there's signals that are on all the time.
Exactly.
And I realize that the more sweeps you get, the lower that minimum is probably going to go. Is that right? It's going to go down.
Exactly.
So it's not the power level that's important, but it's primarily indicated something's on all the time, I guess.
Exactly. And here's a case in point. We see, for example, here a signal that was on in 100% of the 20,000 sweeps that we did. So we know that that signal is in fact on all the time. Here we see that these signals were not on all the time, but they were on a relatively high percentage of the time. Here we're not getting the actual percentage of time that these particular channels were being used, but if we use the tailored land mobile radio system that you guys did for Denver and for Washington, D.C., and that I used many years ago in Atlanta, then you would get those percentages. But you can see that qualitatively, these signals are on a fairly high percentage of the time. And then in here we see that, for example, right in this part of the spectrum, not only was there never, not only do we see that there was some time when there was no signal present in this part of the spectrum, we see that in fact most of the time there was no signal present in that part of the spectrum. So we see that although there was some occupancy in here, it must have occurred for a very small percentage of the sweeps that we made because they didn't even budge the average. And in terms of power levels, yes, these are all measured power levels in decibels relative to a milliwatt, dBm, in the measurement system receiver. And if we want to, we can calculate, and I'll talk about how to do the conversion in a later talk in this series, we can calculate the actual field strength in space that was impinging on our measurement antenna. But here we're just interested in basically these relative power levels.
Now, in some of the lower bands, I assume that impulsive noise could come into effect for that peak. Would it be helpful then to maybe have a median too in the future? Which would kind of help us identify, well, I guess the minimum, you can see that somewhat through the average.
You can see it some, but the question statement is that would it be useful to have median, especially in bands where we see a relatively high background level of noise? For example, if we were getting down closer to say 50 megahertz or so, and I think the answer is yes. It is true that by the time we get up to about 108 megahertz and above, we see less impulsive noise than we might at the lower, more HF type frequencies. But still, with that said, there is some background noise both from natural and man-made sources in there, and I think a median would be of value. I think it's also true that there might be cases where instead of getting a decibel average, we'd like to get a linear power average. So we could even, in principle, get several average curves through here. In fact, in our measurement software, it probably wouldn't be a bad thing to be able to process it for any or all of those, and then display as many or as few of those intermediate curves as we want to get. But definitely that would be a good thing to do. And it is true that by the time you get down to HF, you're actually limited by atmospheric noise. With that, I'm going to conclude the talk for today for the purpose of this tape. Okay, and we can keep talking if you want, but that allows Bill to cut it. Because now the tape's running out, so.
I suppose you could have plots that have, like you say, multiple threshold levels. And